Hello everyone, welcome to CSCN 503, Introduction to Communication Networks. This is Dr. Amr Al-Mugi. To start our discussion of the last layer that we are going to discuss in the protocol stack, which is the data link layer. Let's actually take a look at what we have accomplished in the course so far. So we started this course with an overview of the internet and what the internet architecture looks like. And then we started discussing each and every layer independently. We discussed the HTTP and DNS at the application layer. We discussed web caches. We discussed TCP and UDP at the transport layer and all the mechanisms of TCP. We discussed the IP protocol at the network layer and some routing protocols as well. We have also discussed subnetting and IP addresses, and we discussed the Internet Core and BGP. And so now we reach the final layer that we are going to discuss in the protocol stack, which is going to be the data link layer. We're not going to discuss the physical layer in this course because the physical layer is just mostly about communications, about how signals travel from one place to the other. So our discussion is going to stop at the data link layer. And we're going to stay with the data link layer for a few lectures in this course because there are actually many topics that we can discuss at the data link layer. But we are going to start this discussion today, and hopefully we will be able to let's say, wrap up the discussion of the layers that we have been doing since the beginning of the course. And so we will start with what does the data link layer actually do? So far, all the discussion, all the layers that we have been discussing, we can say that they are end-to-end. So when you talk about an application layer protocols like HTTP, the data is generated at a client, and it is only understandable at a server. And the server is probably at the other side of the world. It's not a local device or a local node that is receiving from the sender. And so the application layer starts at one end, the data is received at another end. The transport layer is also the same. The transport layer is between the sender and the final destination or the final receiver. And so the transport layer is also end-to-end. The IP layer is not exactly end-to-end because every router forwards the data independently, but it's also across several networks. So the network layer is where the data travels from one network to the other. The data link layer is a different one. All the operations of the data link layer are actually concerned with what happens over a single link. And so everything that we are going to discuss in the data link layer is not concerned with anything outside a local network. And the local network can simply be a subnet, so anything that is within a subnet. And the discussion basically ends with the default router that is responsible for this subnet. So here you may have, for example, a bunch of switches and end devices. They are all interconnected, and there is one default router connecting them to the outside world. And so all the discussions of the data link layer are concerned with what happens over one subnet, one local network. This is going to be our discussion. And because it's called the data link layer, well, the data link layer is concerned with what happens over a link. And we have several types of links. We have wired links, we have wireless links, we have shared, and we have dedicated links. And so this is what our discussion is going to involve. What does the data link layer actually do? There are actually several functions. First of all, it does framing, meaning that everything that is generated from the application layer down to the transport layer and then the network layer is put into what is called a frame at the data link layer. Everything that is generated, so you have the application layer data, okay, and you add to it the transport layer header, and then you add to it the network layer header, which is the IP header, and then you add to that the data link layer header. This is the frame. So the data link layer header frames the remainder of the packet, and this is the primary job of the data link layer. In shared networks, so for example, Wi-Fi is a shared network because you have the wireless medium that is shared. So when you communicate with your wireless router, you're communicating actually over a shared wireless medium. And if the network is shared, if the wireless medium is, if the medium of communication is shared, Then there is a function at the data link layer that is called medium access control that basically decides how the medium will be shared, who gets to transmit at which time. This is a very important task in Wi-Fi, and we will actually discuss it very briefly in this course, just to actually see what it's about. There are three other functions that are actually part of the data link layer, and they are actually familiar functions. They are reliable delivery, flow control, error detection, and correction. We know these functions from the transport layer. So we have already seen how these functions are implemented at the transport layer. They are implemented again at the data link layer. And so you may ask why? Why do we need to replicate the functions? Don't we already have them actually at the transport layer? Why do we need to have them again at the data link layer? Consider actually this scenario. You have here the sender, here you have the receiver. These are the two clients, the two end systems. And between them, we have a bunch of routers. So you have several links from source to destination. TCP, for example, when we talk about functions such as reliable delivery and flow control, TCP will handle these functions end to end, meaning that for the sender to detect that a packet is lost, let's say a packet is lost at this router, there must be a timeout, okay, at the sender. And the timeout needs to be long enough such that the sender is sure that the acknowledgement is not simply on its way. And so by default, as we have discussed at the transport layer before, the timer for a packet is typically long. And so it takes a while for the sender to actually detect that something wrong has happened. The reason we implement reliable delivery also at the link level is to recover from errors faster. Now imagine that you have reliable delivery, but within the context of only one link, meaning that when the sender sends something, the data link layer at the sender is communicating with the data link layer at R1, at the first router. Meaning that when something is sent from the sender, R1, the data link layer at R1 sends an acknowledgement. This is, for example, a mechanism that happens in Wi-Fi. Wi-Fi actually has acknowledgements. When you send a data packet to your Wi-Fi router, your Wi-Fi router will respond with an acknowledgement. This is in addition to the acknowledgement that the server will actually send to you. Let's say you're accessing facebook.com. So what will happen is that you will generate HTTP requests saying that you want, for example, your Facebook feed. And so this HTTP request will reach the server. And once the HTTP request reaches the server will respond to you with an acknowledgement. This is the function of TCP. This is end-to-end. But how does the packet actually travel from your device to the Facebook server? First, it goes to the Wi-Fi router, R1. Then it goes to another router in the core, R2. Then maybe another router that is serving Facebook.com, which is R3. And then the final router actually forwards it to the Facebook server. And then the acknowledgement travels in the reverse path. Okay. Now, if your HTTP request is dropped at R2, for example, it will take a while for your client to detect that something has happened. But imagine that your Wi-Fi router will actually respond with an acknowledgement. Now, because we're talking about the context of a single link, the timer at the data link layer need not be long. The timer at the data link layer can actually be very short. And so you can recover from errors much, much faster in this case. This is actually why we duplicate the functions at the data link layer in addition to what we have already at the transport layer. Okay. We will discuss actually two things at the data link layer. First of all, we will discuss the final type of addressing that we have in our network, which is the MAC address. Now, when we talked about functionality, we said that there's something called medium access control. This is a functionality. The address that is added at the data link layer header is called the MAC address. It is named after this functionality, but you shouldn't confuse an address with an actual functionality. In following lectures, we will discuss what medium access control as a functionality is. Today, we're actually discussing the MAC address. Now, the MAC address is also added in the data link layer header. So here there is a source MAC, and there is a destination MAC that is added in the data link layer header by the device that is actually generating the packet. The MAC address is also called the physical address. It is 48 bits long, and unlike the IP address, the MAC address is static and is flat, meaning that the MAC address is actually a property of your device. It gets your device. It comes with the hardware of your device and is not changed. You cannot change it. No one gives it to you except actually your manufacturer. So the manufacturer actually of your device will insert the MAC address as 48 bits and it's not changed. It's also not hierarchical. So for example, when we discussed the IP address, we said that the IP address is 32 bits. Part of it is for the network and part of it is for the host. The MAC address is not like that. The 48 bits are actually divided into two parts. There are 24 bits that define your manufacturer and 24 bits that define or identify your own device. And that's it. There is nothing in the MAC address that would identify your actual network, okay? Which is why we say that the MAC address is flat. And it is also why we say that the MAC address is called the physical address, because it physically identifies your device. It identifies the interface from which you are communicating. Okay? Which is why it can actually violate your privacy. If someone discovers your MAC address, then someone can actually figure out your identity. Fortunately, the MAC address has local context. The MAC address doesn't actually have a meaning outside your own local network. Now, when we discussed these different types of addresses that we have, let's say, for example, you have the communication from the original sender to the final receiver. The addresses that are added, we have the transport layer port numbers, so the source and destination port numbers. These are inserted by the source, and they don't change from source to destination. Okay, so the source and destination port numbers stay the same, even across the routers R1, R2, and R3. IP addresses are also like that. So we know that the source IP address is given to the sender by the network. Your ISP, for example, you get it through the DHCP process, which we have discussed before. So you obtain an IP address and you get the destination IP address through DNS. And so this is how you insert the IP addresses in your packet. The sender inserts those addresses and they stay the same until they reach the destination. So R1 and R2 and R3 don't change the source and destination IP addresses as the packet is routed through them. If you think about it, they cannot actually change it. So for example, R1 cannot change the source and destination IP address because R2 will need this information to know how to forward the packet. So if R1, for example, removed the destination IP address of Facebook and inserted the destination IP address of R2, then R2 will think that the packet is actually destined to it. It has no way of knowing that this packet is actually going to Facebook. And so the source and destination IP addresses are inserted by the source, and they do not change at the intermediate router. Now, the MAC addresses, this is actually where they are different. When the sender sends the packet to the first router, it includes the source MAC of the sender and the destination MAC of the router, of R1. When R1 receives this packet, it will not actually change any addresses at the transport layer or the IP layer, but it will change the source and destination MAC addresses at this time. So R1 will remove the source MAC of the sender and the destination MAC of itself. It will insert the source MAC of R1 and the destination MAC of R2. When R2 receives this packet, it will remove the source MAC of R1 and will insert its own source MAC, will remove its own destination MAC and will insert the destination MAC of R3. Meaning that at every stage, the devices change the source MAC address to become their own and change the destination MAC address to be the MAC address of the next hop. This is why we say that the link layer functions are local. They are for a single link. They have no context outside a single link. So at the data link layer level, there is no awareness of the concept of several subnets, for example. They are only aware of what's happening over a single link. Another thing that we can actually mention is that the type of link between the sender and R1 may actually be a different type of link than between the R1 and R2. For example, between the sender and R1, if R1 is your Wi-Fi router, then this link is actually a wireless link. But the link between R1 and R2 is likely going to be, for example, a fiber optics link. And there are different rules governing transmission over different types of links. And so part of these rules is that the MAC addresses change from one link to the other. At every hop, you have the source MAC address of this particular device that is sending and the destination MAC address of the next hop. So unlike IP addresses and transport layer port numbers, these change every hop outside your local network, because at the Wi-Fi router, your MAC address is going to be dropped, and Wi-Fi router is going to insert its own MAC address in this case. Okay. Unlike IP addresses, the notation for MAC addresses is actually in hexadecimal. So if you have the 48 bits of the MAC address, again, you divide them into groups of 8 bits. But unlike IP addresses, you don't convert them to decimal, you actually convert them to hexadecimal. So if you remember the technical foundation course, to convert to hexadecimal, you take actually every group of 4 bits and you convert them to their hexadecimal equivalent. And so the MAC address is written as a hexadecimal format. Okay, so now we have our packet, consists of application layer data. You have source and destination port numbers, source port and destination port. You have source IP address and destination IP address. And now at the data link layer, you have source MAC and destination MAC. Now let's see what is missing from our packet. We know how the application layer data is generated. For example, it's an HTTP request. It's generated by the client. The client chooses its own source port number, so we know where this comes from. And the destination port number is a well-known port number. For example, HTTP, the destination port number is 80. So we know how the source and destination port numbers are chosen. Source IP address is given to you by the network, or it's fixed. If it is given to you by the network, then it comes through the DHCP. Destination IP address comes from DNS. Source MAC address comes from the device itself. As we said, it's burned on the read-only memory of your device, so it's a physical property of the device. So every device knows its own source MAC address. This is actually the remaining part of our picture. We want to fill this picture today. How does the device know the destination MAC address? And again, I will emphasize in this point, when the device generates a packet and once, let's say this is the sender and this is the final destination or the receiver, the device generates this packet and inserts all the information that we just discussed: the application layer data, source and destination port number, source and destination IP address, and the source MAC. It wants to insert the destination MAC, and the destination MAC is going to be the MAC of the first router, R1. And R1 will remove the source and destination MAC, will insert its own source MAC and destination MAC of R2, and then R2 will insert its own source MAC and destination MAC of R3, and so on. So every device knows its own source MAC, so the remaining part of the picture is how each device will actually discover the destination MAC of the next hop. And this is where we reach the final protocol that we will discuss in this course, which is called the address resolution protocol. The address resolution protocol is a way for devices to discover the MAC address of a device that they already know the IP address of. So you have a device that you know its IP address and you want to discover its MAC address. Now, to use ARP, you will need a broadcast MAC address. So we already know the broadcast IP address. So for IP, the broadcast IP address is all ones. So it's 255.255.255.255. At the data link layer, there is also a broadcast MAC address, which is also all ones. And so all ones will be FFFF. So 48 bits, all ones. Okay. So let's say you have this device wishing to send a packet to this device. It knows its IP address, but doesn't know its MAC address. So it is going to actually use ARP to discover the MAC address in this case. So what happens? This device here, which is the sender, wants to discover the MAC address of this device. So what it does is that it sends something called an ARP query. Okay, the ARP query is nothing but a packet. It has actually a source IP of the sender, destination IP of the device that you want to discover its MAC address, the device's own source MAC. Okay. Now, what do you think the sender should actually insert as the destination MAC? Obviously, it doesn't have this information. It wants to discover the destination MAC of this device, 137.196.7.14. It wants to discover its MAC. So the ARP query is basically a question in your network. It says, whoever is, the sender will actually broadcast the ARP query within the local area network, within the local network. Basically, the ARP query is a question that says, whoever owns this IP address, please send me back your MAC. And so the ARP query is a broadcast packet. So we have already seen some types of broadcast packets like DHCP, for example. The DHCP Discover and request packets are broadcast packets. And now we have the ARP query, which is also a broadcast packet. It is broadcasted in the network, having a destination MAC address all ones. Now, because it's all ones, everyone in the local area network will receive it, but only the one that owns the destination IP address will respond with an ARP reply. Now, the ARP reply has also the same fields. The source IP address is now going to be the address of the one that received the query and is responding to it. So it's going to be 137.196.7.14. The destination IP is going to be the IP address of the one that is requesting this MAC. And then the source MAC address is going to be of the one that is now sending the packet. It's going to be this MAC. And the destination MAC address is going to be the one from the ARP query that was a source MAC in the ARP query. Okay. And now, because all these fields are filled, the ARP query is actually unicast. This is actually what is special about the address resolution protocol. The ARP query is a broadcast packet. The reply is a unicast packet, meaning that only the requesting device will receive the ARP reply. The ARP query is received by everyone in the local area network. The ARP reply will be received only by the requester. And now the requester is going to have the MAC address of this destination, which is in the source MAC of the ARP reply. So what will the requester do with it? It will actually save it in something called an ARP cache. It will save it as an entry. The entry in the ARP cache says that the device that has this IP address also has this MAC address. Typically, addresses in the ARP cache expire after about 20 minutes. Now, you may ask, why should an entry in the ARP cache expire? Why shouldn't it just stay there forever? Well, because IP addresses are not permanent. So a device that has this MAC address and now has this IP address may later have a different IP address. And so the devices need actually a mechanism to make sure that this IP address is currently associated with this MAC address. And so right now, the device has discovered this mapping between IP and MAC, and so it will insert it in an ARP cache. If the same device wants to send a packet later to the same destination, it will consult its ARP cache. If it finds an entry there that has not expired, it can actually use it right away, so it doesn't need to do ARP once more. If there is no entry there, then it has to do ARP again. Now, just like everything in the data link layer, the ARP protocol is actually a local protocol, meaning that everything that we have discussed about ARP happens within the scope of a single subnet, within a single local area network. You cannot actually discover a MAC address in a different subnet. You cannot send an ARP query for a different subnet. So what happens if you have a situation like this? You have actually device A wishing to send a packet to device B. Now, if you look at the IP addresses of devices A and B, device A has IP address 193.154.112.111. Device B has 222.182.191.009. Obviously, the two IP addresses are in two different subnets, and the ARP process is local. So what actually is going to happen? Because B is in a different subnet, A will actually have to send the packet first to the default router. And the default router is going to look up its routing table to find how to reach the destination B, and will decide that it's going to use this port to reach B, and then it's going to put the packet to B. Now, we will assume that the application layer data, the transport layer port numbers, and the source and destination IP addresses have been discovered by A. So A creates a packet, and now it wants to send the packet to B. It knows the source and destination port numbers, knows the source and destination IP addresses. So we'll assume actually that it knows the IP address of B. It knows, obviously, its source MAC address. But now it wants to send the packet to B. Now, A has a decision to make. If the destination, which is B in this case, is within the same local network, then it actually can send an ARP query to just actually figure out the MAC address of B. Once it figures out the MAC address of B, it can send it right away if it is within the local area network. Obviously, in our scenario here, this is not the case. B is in a different subnet. So For A to proceed, now what it has to do is that it has to send the packet first to the default router. So the packet that A will send will actually obviously contain application layer data, port numbers, okay, IP addresses, which is the IP address of A and B, and source MAC of A. Destination MAC should be that of the default router, which is this one. Okay. Now, how should A figure out the MAC address of the default router? It can't unless it does ARP first. So before A can send the packet to the default router, it will send an ARP query not to discover the MAC address of B, but to actually discover the MAC address of the default router. So the ARP query that A will send will contain its own source IP address. The destination IP address will be that of the default router, its own source MAC, and the destination MAC will be all ones. Okay, because the ARP query is a broadcast packet. Everyone in the LAN will receive it, including the interface of the default router that is associated with the subnet. And it will respond with an ARP reply that has the source MAC address of the default router, the destination MAC, the source IP address of the default router, destination IP address of A, source MAC address of the default router, destination MAC address of A. And now this packet will travel to A, and now it can actually send the packet with the destination MAC address of the default router. And again, I will stress that the packet that is sent from A has the source and destination IP addresses of A and B. Okay. Now, the default router will receive this packet. It will find the destination IP address of B, and now it will consult its routing table to figure out how to forward the packet to B. And so now the router needs to actually send the packet from this interface to B. So what will actually the router change in the packet? The application layer data stays the same. Source and destination port numbers, the router does not touch them. Source and destination IP addresses remain that of A and B. The source MAC in this case should actually be that of the default router, and the destination MAC should be that of B. But how will the router, actually we're talking about this interface at the router, how will this interface discover the MAC address of B? It will actually have to do ARP once more. It sends an ARP query as the source IP address of the default router, destination IP address of B, which it gets from the original packet that A sent to it. This is actually why it has to actually have the destination IP address of B. The ARP query will also have the source MAC of the default router, and the destination MAC will be all ones because it's a broadcast packet. Everyone in the network will receive it. B will actually also receive it and will respond with an ARP reply. The ARP reply will contain the source IP address of the default of B, destination IP address of the default router, which is this one, the source MAC address of B, and destination MAC address of the default router, meaning that the ARP reply is a unicast packet back to the default router. Now the default router has the MAC address of B. It can then forward the packet to B. So again, just to actually recap this entire process, A wants to send the packet to B. B is in a different subnet. So in order for A to send the packet to B, it has to send it first to a default router. Whenever your final destination is in a different network, your next hop is a default router. And so for A to send the packet to the default router, it will insert the source and destination IP address of A and B, the source MAC address of A, but now it needs to discover the MAC address of the default router. It discovers it through ARP, sends an ARP query. The interface of the default router that is associated with A will actually send an ARP reply back to A. And now A sends the packet to the default router, and now the default router wants to send it to B, but it doesn't know the MAC address of B. And so now the default router, again, now we're talking actually about the second interface of the default router, will then send an ARP query to discover the MAC address of B, gets an ARP reply, and then forwards the packet to B. This is actually why every interface of the default router needs to have a different IP address and needs to have a different MAC address, because it's as if they are two devices. They are in two different subnets, and so they need to be identifiable separately for each subnet in this case. This is basically the ARP process, and now we have completed the picture of every field in the headers from application down to the data link layer. Okay, and now we can actually understand more about the functionalities of the different devices. This is actually why the host and the sender and the destination needs to have the full protocol stack from application down to physical. The router, because it does routing based on a routing protocol which uses IP addresses, need to have network data link and physical. Okay. At the network layer, this is where the routing protocols operate. This is where we have subnets. This is where we have subnet masks. And so the router needs these three layers. Switches, because they are local network devices, they only have data link and physical layers. And later in the course, we will see actually how a switch forwards the packet based on MAC addresses. Okay, and so before we actually proceed to anything else, for the remainder of this lecture, we will actually see an example that sums up all the protocols that we have seen in this course so far. Basically, we have an example that sums up all the networking components that we have been discussing. We have here Bob, who have just signed in to his network. Let's say this is actually the GUC network. Bob has just signed into the network, and Bob wants to actually retrieve the web page of www.google.com. Now, Bob has internet or will get internet connectivity from the GUC network, and the GUC network gets its internet connectivity from an ISP, from an internet service provider. So the local DNS server that Bob is going to be associated with is right here. Now, we want to be able to see the process of how actually Bob will finally actually generate application layer data. It will generate transport layer header that has source and destination port number, will generate an IP header that has source IP and destination IP, and will generate some kind of data link header that has source MAC and destination MAC. We want to see the entire process until actually Bob gets the HTTP reply from www.google.com. We'll start from scratch. Bob has nothing. Bob has just joined the network. So obviously Bob only has a MAC address. This comes with the device of Bob. Bob has not yet logged into the GUC network. And so Bob will start the process from scratch. So the first thing that Bob needs to do before actually he is able to send anything to the network is that Bob has to actually obtain an IP address. So the first thing that Bob has to do is to send a DHCP Discover packet. The DHCP Discover packet will have 68 and 67 as source and destination port numbers. These are fixed for DHCP. Source port number is always 68, destination port number is always 67. The source IP address is all zeros, as we said, because Bob still doesn't have an IP address. He will use the all zeros IP address to discover the DHCP server. Destination IP address is all ones because it's a broadcast packet. Source MAC address is that of Bob. Destination MAC address is again the all ones because the DHCP Discover packet is sent to everyone within the GUC network. So it's broadcast within the GUC network saying, whoever is the DHCP server, please respond to me. And so if you review the DHCP process, it's a four-way handshake, which ends with the DHCP server responding back to Bob saying, actually, this is now the IP address that you can use. And the entire exchange in DHCP is broadcast packets. So everything that is actually broadcast through the entire network. And at the end of the DHCP process, Bob now has an IP address that is assigned to him by the GUC network. And you will see that Bob has an IP address which is 68.85.2.101. It has the same network address as the GUC network in this case. Okay, so now Bob has an IP address. Now, obviously, the end goal is that Bob wants to establish a TCP connection with google.com and send it an HTTP request. So where would Bob actually send the TCP connection request? Bob now has a source IP address, but Bob doesn't have the destination IP address of Google. So before Bob can actually establish a TCP connection with Google, now Bob has to discover the destination IP address. And so how do devices discover the destination IP address? They have to go through a DNS process. So now Bob has to send a DNS query. Okay, this DNS query will have the URL of Google, will have Bob's IP, destination IP will be that of the DNS server, destination MAC will be that of Bob, and source MAC will be that of Bob, and destination MAC, we will talk about it in a little bit. But first of all, obviously now Bob has the URL of Google because Bob knows exactly which server he wants to access. Bob has an IP address, the source IP address is known. Where does Bob obtain the destination IP address, which is that of the DNS server? Bob actually obtains this information from the DHCP process. So part of the DHCP process is once you actually get the IP address, the DHCP server will give you a bunch of useful information, such as the IP address of your web cache, the IP address of your local DNS server, the IP address of your default router. This is actually very important. So through DHCP, Bob will actually discover the IP address of the default router as well. And Bob will also discover the IP address of the DNS server and the subnet mask of his network as well. Okay, so when Bob wants to send the DNS query, Bob will actually know the destination IP address of the server. And so the remaining field in the DNS query is the destination MAC. So which destination MAC address should Bob actually insert in the DNS query? Now, by examining the destination IP address of the DNS server, we find that it's 68.87.71.226. So obviously the DNS server is in a different subnet than Bob. And so Bob knows that if he wants to send a packet such as the DNS query to another device that is outside the subnet, then Bob has to actually send the packet to the default router. And so before Bob can send the DNS query, Bob has to send an ARP query to discover the MAC address of the default router. So Bob sends an ARP query, contains his IP address, destination IP address of the default router, which he gets from DHCP. This is why DHCP process is actually very important. The information that you get from the DHCP process allows Bob to perform all the networking tasks that he wants. Source MAC address in the ARP query is that of Bob. Destination MAC address is all ones because it's a broadcast packet. Everyone in the GUC network will get it. The default router will reply with an ARP reply, which is then unicast back to Bob. And so now Bob has the destination MAC address of the router. Bob can now send the DNS query to the default router, and then the default router will forward it to the DNS server. Now, there are obviously steps in the middle. So when this router here wants to send the DNS query to that router, if it doesn't know its MAC, then it has to do an ARP process again, and it goes on until the packet reaches the DNS server, but I didn't obviously insert all of that here. The DNS query reaches the DNS server. If it doesn't have the translation itself, then it has to go through the entire DNS network, the root and TLD and authoritative DNS, and finally it will actually get the translation and send it back to Bob. And so now Bob has the destination IP address of google.com. And so now Bob is ready to establish a TCP connection. Now, Bob will send the TCP connection request to google.com. And first of all, Bob will examine the IP address of google.com and will find that it's in a different network than Bob. And so Bob will have to send the packet to the default router. And so the TCP connection request will have the source port number that Bob chooses for this session. Destination port number is 80 because it's HTTP. Source IP address of Bob, destination IP address of google.com, source MAC address of Bob, and destination MAC address. You will see that this is actually the destination MAC address of the default router because the packet is going outside of the local network. Now, at this time, where does Bob get the destination MAC address of the default router? Because Bob has already done an ARP process before when Bob wanted to send the DNS query. So now when the first ARP process is finalized, Bob will have actually the MAC address of the default router, which he will save in the ARP cache. So when Bob comes to send the TCP connection request, the entry will already be in the ARP cache, and Bob will not actually have to do an ARP query again. Now the packet goes to the default router, which it forwards through routing protocols until it reaches google.com, and google.com will respond with a TCP HTTP response. Now you actually see the entire process. You see how everything in this little network is connected, even though google.com is on the opposite side of the world. When Bob establishes a TCP connection, it's actually a logical connection between Bob and the Google server. When there is congestion control, it's actually through the feedback from the Google server back to Bob. When there is a reliable delivery, it's because acknowledgements are sent from the Google server back to Bob. All the processes are happening at the transport layer, are happening end to end. At the IP layer, every router is actually having a routing protocol that is figuring out how to actually send the packet to a different network in this case. And so every router interface is part of a different subnet. This router, for example, has two different interfaces. This is one subnet, this is the other. Every subnet is associated with a network address and a subnet mask. And so devices within each subnet will know that if it wants to send the packet outside the subnet, it will have to give it to the default router. And so at the data link layer, the MAC addresses are local. Every device knows its own source MAC address. And if it wants to send the packet within the subnet, then it can actually do ARP and discover the destination MAC. And the switches will do the forwarding right away without needing the router. If the packet is going outside of the subnet, then it has to go to the default router first. And so you have to do ARP to discover the MAC address of the default router. How do the sending host obtain all the information about the network, such as the address of the web cache, the address of the default router, the network address, the subnet mask, the local DNS server? All of this is done in the DHCP process. When the client finalizes the DHCP process, not only will he have an IP address, he will have all the information necessary to do all the networking functionalities in the future. This is basically how everything in the course is interconnected. This is basically how all the protocols are joined together in order to play different roles such that at the end of the day, you can actually send your HTTP request and receive a response back from whichever server you like. We will stop our discussion here today. Next time, we will discuss other issues related also to the data link layer. Thank you. Stay healthy. Stay safe.